was busy suffering through a Brownies game.
Oh, I'm sorry. Phew, that is suffering.
Browns game where they lost to a team they shouldn't have lost to because their coach sucks. No, I heard
Brackets, I know.
Yeah. I heard Williamsville won, which is pretty cool.
How's the break?
Good.
Not long enough. Is it ever long enough? Let's be honest, is it ever long enough? I do apologize for not being here. I was still rather kicked off about it. It's the first time in 21 years.
Your doctor literally called you, don't go in.
Yeah, I have a bunch of buddies that went to the
Otherwise, I would have been here.
Like when they were in high school, it was like 4 or 5 years ago, I think. They like played second stage. So like this is like I think a really big deal for Williamsville if they won. But I saw Rochester won again.
That never happened.
Yeah, I know.
Played about 8 times in 10 years or something stupid like that.
It's almost like they recruit or something, Dr. Joe.
Yeah, I can't. That would never happen. What's that?
I said my high school one was to state like every
They're usually pretty good, they just never go. See,
they get big hits, and when they get to like the playoffs, they're like, oh, we can only do these big plays, and then that's how they lost last time to state. They would just like advance little by little.
right. All right, so let's look at a little bit of new stuff that goes along with some of the old stuff that we talked about last time. So, last time, it's been a while, I know, we talked about how we did transformations of one variable to another. Where there's a nice theorem in the book if you really care about the theorem in the book. But remember, all we did really was just look at the distribution function and go from the distribution function and work from there to get the PDF for the transformation. Because I know it's been a little while, but that was what we did. So what this stuff talks about, this goes with section 5.2 in your text, is talking about transformations with functions of 2 variables and doing the transformations that way. And like I said, this should remind you quite a bit of Calc 3 of doing transformations of integrals when you did changing coordinates of double integrals into either polar coordinate, well, not either, double integrals into polar coordinates or triple integrals into cylindrical or spherical coordinates or arbitrary things, right? When you talk about putting the Jacobian in there. And basically what the Jacobian is just a factor that talks about how your areas of rectangles get changed when you do the transformation from one to the next. Or volumes of the boxes, how do the volumes get changed as you go from one set of coordinates to the next. I mean, that is the idea, right? If you think about cylindrical coordinates, if you think about it from Calc 3 perspective, you're taking a little box. Wow, that is a terrible looking box. Okay. Taking a little box and then changing it basically into a piece of a pie slice like this, right? Right? Where it gets, basically everything gets a little bit wider as you go out. And that's why you have to do that extra R piece in there, right? Well, cylindrical is still R, right? The spherical is when you get rho squared sine phi. Good. I still remember it. Good. That's wonderful. Fantastic. All right. So the same kind of thing is going to happen here. And again, probably from what you remember from the Jacobian, is one of the things you have to worry about is what happens with the boundaries. So we have the same kind of issues here. So let's just run through this. This also has another concept that's going to pop up in the next section as well, and talking about doing things with independent random variables. So this says that x1 and x2 both have identical PDFs. They're independent and identically distributed. They both have the same exponential distribution. And this one asks us to find the joint density of the two. So y1 is equal to x1. So x1 is not really changing. It's y2 is what's really going on here. It has some sort of a change going on with it. All right. So when we change one from the other, let's figure out first what is the joint PDF of x1 and x2. Let's start there. How are we going to figure out what that is? Well, what are we given about x1 and x2? They're independent, right? So if they're independent, if I know each of the distributions for x1 and x2, how can I find the joint? What do I do with each of the PDFs? Multiply them, right? So for this one then, our f of, we'll call it f of x1, x2, will just be e to the negative x1 times e to the negative x2. They're identically distributed. I'm just calling 1x1 and 1x2, right? If I really want to be fancy, I can add my exponents together and make it e to the negative x1 plus x2. We agree? All right. So that gives us our joint PDF for x1 and x2. I want to change this now to a PDF of y1 and y2. Well, the easiest way to do that would be to, well, I can certainly substitute just y1 in for x1 because it says y1 is supposed to be the same thing as x1, right? Now for x2 though, what do I need to do? Well, I need this as a function of y1 and y2 and plug it in here. Just like what you did in Calc 3 when you did your change of coordinates, right? Like for example, if you change to polar, what do you plug in for x? R cosine theta, and for y, r sine theta, right? You have x equals something in terms of r's and thetas, y equal in something in terms of r's and thetas, and you plug it in, right? Same idea here. I need my x1 in terms of y1 and y2. I need my x2 in terms of y1 and y2. Well, I already have x1 in terms of y1. What would x2 equal then?
y2 minus 2y1 over 3.
Cool.
I think that's right.
I think so. So far, so good? All right. So then we know now what to plug in for x1 and x2 in here to figure out this part of the PDF, right? We agree? Okay. But what this transformation doesn't do is it doesn't take into effect how these areas have changed or volumes have changed depending on what dimension you're in. In this case, it's just areas because we're just doing functions of two variables, right? So that's where the Jacobian comes in. Remember how to calculate the Jacobian? Yeah, you make a determinant of partial derivatives, right? I got to do the partial of x1 with respect to y1, right? I do the partial of x2 with respect to y1. Oops. And the same things, but this with respect to y2. Remember doing those? And then technically, I need to do the determinant, but I also need to make sure everything's positive, right? Because I'm changing areas to areas or volumes to volumes. So I'll do the absolute value when I'm done, make sure everything's positive. Right? Okay. So in this case, what is the partial of x1 with respect to y1? 1. What is the partial of x2 with respect to y1? Okay. partial of x1 with respect to y2, 0, and with respect to partial of x2 with respect to y2, 1/3. So when we do the determinant, you get 1/3. So basically what this, if you were thinking about what happens to squares, and think about it in unit squares, whatever you want to think about it as, when I take that square and transform it, the area of that square gets shrunk by 1/3. A third of what it used to be. Okay? Pardon me. All right. I would do the absolute value if I need to. If this were negative, it's not in this case. But if it were, you would do the absolute value. Okay? All right. So then our new PDF, I'll call it G of y1, y2, will be our f of whatever I'm going to write it in terms of the kind of arbitrary function ideas. So let's say this is h of y1, y2, j of y1, y2 times the absolute value of the Jacobian. So this is of just a function representation of x1 in terms of y1 and y2. This is a function representation of x2 in terms of y1 and y2. Just writing it as fun. I'm just trying to write it as general as possible, but just remember I've got to solve for x1, I've got to solve for x2, and then just plug it in. Okay. All right, so in this case then, x1 is the same thing as y1. x2 was y2 minus 2y1 over 3, if I remember correctly. And then times 1/3 on the outside. Oops. Remember our PDF for x1 and x2 was e to the negative x1 plus x2, right? So I'm taking out the x1, putting in y1, taking out the x2, and putting in y2 minus 2y1 all over 3. And if you simplify that, you get 1/3 e to the minus y1 plus y2 over 3. Just getting a common denominator there. Oops, yeah, that's right. I made a mistake for a second, but okay. All right, so if I scroll back up, because I need to look at my options, it's one of those two, right? Because those have the right forms for the PDFs. We agree? It was one of those two? Okay. So it's a matter of which one is it? Okay. So let's think about it for a minute. We know that x1 and x2 were independent exponential random variables, right? So what are your bounds for x1 and x2? Zero to infinity, right? We agree?
Yeah.
So in particular, let's look at this. Your y1 has to go from 0 to infinity without any doubt, right? Because x1 and y1 are the same. Right? Okay. Now let's look at your y2. What's the smallest x2 can be? 0, right? So y2 has to be at least as big as what? 2y1, 2x1 or 2y1 in this case, right? So y2 has to be at least as big as 2y1 because x2 can't be negative, right? So which of those says that y2 is at least as big as 2y1? E does, right? So that's how we got E. Everybody see what I'm saying? I didn't write it down, but you see what I'm saying? Right, so basically we're analyzing the boundaries, much like what you had to do when you did this in Calc 3, changing your integrals, right? Because the whole point of doing this transformation of coordinates from one system to another, for our purposes, we're doing transformations of random variables and trying to morph one distribution into another. There's lots of reasons why you might want to do that, mainly for simulation purposes, if you're trying to do random samples and not just making, basically when you do something on the computer, it gives you a random number between 0 and 1, is one of the most common functions. That means that you've got a uniform distribution between 0 and 1. Well, for a lot of simulation purposes, you're not going to deal with uniform distributions. So you got to talk about how you transform that uniform distribution into a distribution that you're actually looking at. Okay? It's called Monte Carlo simulation, one of the things it's used for. Much like what you do in Calc 3, you worry about what the bounds have to be, right? Because you're changing your bounds on your integrals. And you can see where that might be important here for calculating probabilities, because when you calculate probabilities, you're doing integrals a lot of times. Okay? So that's why we have to pay attention to these bounds. And essentially what this did is it takes a rectangular region, as much as infinite area can be a rectangle, but it changed it into a triangle, right? Do you agree? Does that make sense? It changed that whole entire rectangle into a triangle? Yeah, Megan?
So the 2 is in front of the y1 because it's in front of the 2, or it's in front of the x1?
Right, because the x1 is the same thing as y1 here.
Yeah.
So if I plug it in there, that's why the 2 is in front of the y1. And the reason why we wanted to make sure it was bigger is because this can't be negative. Yeah. So my y2 has to be at least as big as my 2y1. That's where that comes from. This one okay? This process is the same, by the way, for all of these problems. The thing that gets tricky is what happens with your regions. So let me focus on that for just a second. I want to erase some of this so I don't have to. Maybe I'm going to erase it. There it goes. Kind of. I don't know why it's so clunky sometimes to erase. All right. So if this is your x1 and this is your x2, this is the region that's our region of support, correct? Okay. When we do our transformation, when you have y1 and y2, your y2 is at least as big as 2y1, so you've got this line, and you're talking about this region. So you're transforming what looks kind of like a rectangle, and like I said, as much as it can be a rectangle since it's infinite, right? But it's changing that rectangle into this triangle. And you can kind of see where the 1/3 piece comes in, right? I mean, again, it's infinite pieces, but it really does look like it chopped it into a third. Right? So you can kind of see where that 1/3 in Jacobian comes in as well. Does that make sense? As much as it kind of can make sense as far as doing this infinite ideas. But basically what this is doing is, just generally, is just taking, it leaves this axis basically alone and smashes this way. It's not quite what's going on, but it's just kind of rotating a piece of dough, making it a little bit smaller. This one okay? Same idea when we're doing any of these, by the way. So let's just do another one. This is 29.1. All right, so this one we have to do a little bit of extra work because we're not looking for a joint density function of z with something right now. We're looking for the function of z. So we're going to have to do an extra step here to figure out this density function for z. All right, so what we do a little bit is actually cheat, okay? So we have our z is equal to xy. Let's let w equal x. And I want to transform this PDF of xy into a PDF for z and w. Start there, just like we did in the last problem. So what do we need to do that in this case? if I want to change this from f of xy to a g of zw, what would I need to do? What did we do the first time? Well, I'm going to have to find the Jacobian. Before I do that, I still have to do one more thing. Yeah, so I have to have my x equal something and my y equal something, right? I got to solve for x and y, don't I? I'm going to do the inverse of the transformation. Well, what is x equal to? W. And if x is w, what's y? Good. Okay. So that's what I have to do first. I have to do the inverse transformation, right? We've got z in terms of x and y. I need x and y in terms of w's and z's. Right? I got to do the inverse. Now I do the Jacobian. I got to do the partial of x with respect to w and z. I got to do the partial of y with respect to w and z. Right? It doesn't really matter, since we're doing absolute values, it doesn't really matter if you go, it doesn't really matter if you remember to go across rows or down columns when you do these, by the way, because all it does is transpose the matrix and it doesn't do a lot to the determinant. As a matter of fact, taking the transpose does nothing to the determinant. Okay? So, and you might flip a row, but flipping rows or flipping columns, all that does is make it negative. For those of you taking linear algebra next semester, you'll learn that. Okay? Yeah, you'll have me for that too. Isn't that exciting? All right, so if I do the partial of x with respect to w first, what do we get in the upper left-hand corner? 1. Take the partial of x with respect to z, what do we get in the upper right-hand corner? It doesn't matter. Or if I do the y with respect to w, it doesn't really matter as long as you're consistent, right? If I do x and z here, that's okay. If I did x and z this way, it's okay. Really doesn't matter. As long as you're consistent, it does not matter. Okay? Partial of y with respect to z. 1 over w. Partial of y with respect to w. Actually, I did that. I'm not consistent. I just said be consistent, didn't I? Where did this 1 come from? The w. So I better do the w first here, right? So minus z over w squared. I got to do the derivative of 1 over w. And then 1 over w over here. What do you get for the Jacobian? 1 over w. Do we have to worry about absolute value? No, because x is the same thing. X and w are the same. What's x go between? 0 and 1. So my w will go between 0 and 1 as well.
You have to worry about the fact that x.
Yeah, that makes it a little weird. Okay. We're just going to let it go off to infinity. It'll be fine. Yes?
So, why do we have to set w to x? Like, do we need another variable to go with it?
We'll need another variable to be able to do the Jacobian. Yeah.
Okay.
And we'll get rid of the w in a minute. Okay. We're going to introduce it and then get rid of it. Okay. It's lots of fun. Okay. All right. So what's our g of z comma w going to be then? That'll be f of z is xy. And, oops, sorry. Try that again. X is w and y is z over w. Right? This is x, this is y. I'm plugging in the inverse transformations there. What was the distribution? It was x plus y. So this will be w plus z over w. And then what do we have to multiply this by? We have to do that too. 1 over w. So we'll get 1 plus z over w squared for our joint PDF. We agree? Okay. Yeah, Megan.
Why are you multiplying by 1 over w?
Because remember we have to multiply by the Jacobian. Yep. It's all right. So far, so good? Okay. I forgot my watch today, so I was looking at my phone. So I had to bring it for a while. And I figured you probably don't need to know what time it was when we end, because otherwise I might just keep going. Or rely on Haley to hold the stop sign. All right. This is not what the problem asked for. The problem asked for the density function of z, right? Which means I need to get rid of the w. Basically, we have a joint PDF. I want to find the marginal for z. Okay? To find the marginal for z, what do we have to do? Yeah, integrate over all the w's, correct? Right? Now, what is w the same thing as? X, right? What does x go between? 0 and 1, so w is going to go between 0 and 1, right? Okay? We should be a little bit careful, make sure that we don't have any weird bounds, right? Because we know we've changed rectangles into triangles before, right? If x goes between 0 and 1, and my y goes between 0 and 1, my z also still goes between 0 and 1, right? Because I have lots of flexibility for my y's as well as my x's. So we should then get that our marginal for the z's, which I'm going to use h, will be the integral from 0 to 1 of the 1 plus z over w squared dw. Okay. That's a problem. Then it should be a w anyway, but that's still the problem. What did I do wrong? Okay, where did I go wrong? Why is that a problem, by the way?
Divide over 0.
Yeah, it's a 0 in the denominator, correct? Let's see, what did I do?
Can't we take the 0 to be 0?
My bounds. Make sure my bounds make sense. Now let's make sure that we have the right bounds. Because it could be the bounds as well. So usually when you're worried about doing these transformations, you look at what happens to the boundaries. All right? So let's do the easy boundaries to start with. Let's look at, let's say this is x and y. What happens if x is equal to 1? Then w is 1. So if this is z and this is w, then w is 1, and z goes from 0 to 1, right? If x is equal to 1, I just said that. If y is equal to 1, what happens? Z equals x, right? Z is x and w is x, so z equals w. Yeah, my bounds are different. That was my problem. Right? We agree? What happens if x is equal to 0? It's 0, 0, right? If x is equal to 0, this point it can completely collapse, didn't it? And then if x is equal to, or excuse me, if y is equal to 0, then you get w goes from 0 to 1, right? So if x is equal to 0, your z is equal, excuse me, if y is equal to 0, z is 0, correct? And your w goes from 0 to 1, which is this piece here. So this is the region, right? So I had to be careful with my boundaries. It didn't just go to the rectangle 0, 1, 0, 1 again. We had an entire piece that collapsed. So going back down here again, Yeah.
Why does Z equal W for the second part?
So if you do the y equals 1 here, then you get z equals x and w equals x, which means that the z is equal to w. That's where that line comes from. All right, so if I want to integrate and get rid of the w's and hold the z constant, what does w go between? It's not 0 and 1 anymore, it's z and 1, isn't it? Yeah, that makes me much more happy. That helps, doesn't it? Gets rid of that 0. So we'll get 1 minus z minus z minus 1. So we'll get 2 minus 2z. Yeah.
Can you explain now the two boundaries of when, because I get when x is 0, the whole thing is 0.
Okay.
But why would-
Okay. Just draw the picture down here again, so I'll just scroll back up. That far enough? Okay. Sorry. All right, so you've got boundaries of, this is y equals 0, x equals 1, y equals 1, x equals 0. So you've got z is x, y, and w is x. I could have made w y, by the way, that I just chose one, so you make it easy to do the transformation. All right, so here's my z, here's my w. When x is 1, we just get z equals y, w equals 1. And we know that y goes from 0 to 1, so we just get basically a parametric representation of that line segment. Okay. When y is 1, we get z equals x and w equals x, which means that z is the same as w going from 0 to 1. That's where that comes from. Okay. When x is 0, we get z is 0 and w is 0. So we just get that point. So this entire thing just collapses to a single point. And then when y is 0, we get z is 0 and w is x. So that's where this one comes from here. Yeah, that's where it comes from. Yeah, great.
How do you know that W is on the y-axis?
I don't. It doesn't matter. I could write it the other way too. It really does not matter. All it would do is just invert where the picture is. In fact, it might be more sense to put W here and the Z there, and it makes the picture look a little bit nicer, I think. But it doesn't matter. I just put it there because I wrote it second. This one okay? Sorry about getting that boundary confused, but you can see why the boundaries are also important. Grace.
How do you know that you're shading up instead of down?
How do I know that I'm shading up instead of down? Oh, that's a good
Never
question.
mind.
That's a good question, but it's basically because that's where the boundary hit land. So it bounded that, has to bound that area. But you can check it just by plugging in some points. Your, in particular, your Z has to be less than your W because you're taking a number between 0 and 1 and multiplying it by a number between 0 and 1, so it has to be less. So it has to be over here. This one okay?
Is that the answer to the question?
Yeah, and the density function, this was your answer here.
Is it multiple choice?
No, it wasn't. This one just had to find the density function. Gonna do another one like that one? Okay. Huh, shockingly enough, I had one lined up. Surprise, surprise. All right, let's look at 29.5. I keep looking at my wrist thinking I'm gonna see the time. All right. So same kind of setup. We want to find the density function for W, where W is x times y. So we're going to do the same kind of trick. We have our W is equal to xy. Just pick something for your z. Make it easy, so make it either x or y. Which one do you want to do? X, okay, sounds like a plan. We're only doing this so that we can find a joint PDF to start with. And then after we find the joint PDF, we'll integrate the Z out to find the marginal for W, just like we did in the previous one. Okay. It's the only reason why we're introducing this extra function. Does that make sense? Okay. All right. So then, just like we did before, I need to solve this for x and y, which is not hard. X is Z, so what does y have to be? W over Z. What do we do next? Jacobian. So you tell me what to fill in for the Jacobian. 1, 0, okay. And again, it doesn't matter. It doesn't matter if you do the x's across or x's down, as long as you're consistent. So if this is the derivative with respect to z, this is the derivative with respect to w. Do the same thing with your y's. Reason why it doesn't matter is because we're going to do the absolute value anyway. At worst, it happened is you've made it negative rather than positive. Okay. So what's the second one then? Okay. Okay. And we get 1 over z. Do I need to worry about absolute value here? No, why not? Because z is never negative, right? Z is the same thing as x, and x is between 0 and y, right? Okay. So now if we find our joint PDF, I'll write it as z comma w. It doesn't really matter if you do zw or wz. It doesn't matter. Because we're going to plug this into f. What are we plugging in for x? Z. What are we plugging in for y? W over z. Right? And we're going to multiply this by 1 over z. So we get 8 times z times w over z times 1 over z. I've plugged in everything correctly. So that gives us 8w over z. We agree? All right. So now we want to integrate this with respect to what? Z, over all possible z's, correct? This is where it comes into play again, where we need to worry about the boundaries. So we know that we had 0 was less than or equal to x, was less than or equal to y, was less than or equal to 1. So x is less than or equal to y is over there, right? So we've got 3 boundaries to worry about, don't we? We've got, this is y equals 1, this is y equals x, this is x equals 0. We agree? So let's transform this then. Now remember, our z was x, y, and w was x, right? Or did I did that backwards, didn't I? W is x, y, z is x. Sorry. So what happens when x is 0? Yeah, z is 0 and w is 0. So I get 0, 0. Yeah. When y is 1, what do we get? W equals x and z equals x. W is z. And what happens if y is x? Yeah, w is x squared, so w is equal to z squared, right? Get that? By the way, hopefully it makes sense that this is two pieces, two boundaries essentially instead of three. Why is it two instead of three? What happened to this entire boundary? It went to a point, right? It completely took this boundary and smashed it to a point. So it makes sense that we only had two bounding curves now instead of three. Right? What do we need to integrate over? Z's, right? Which means I need to hold my W constant. So this is W equals Z, or Z equals W, I should write it that way. And this is W is Z squared, right? So this is Z equals square root of W. Right? So when we find our function now, our h of W, we want to integrate from what to what? W to square root of W of our 8W over Z dz. Antiderivative is going to be natural log of Z. So we get 8W natural log of square root W minus 8W natural log of W. Why am I getting something that's negative? What did I forget to do? That's two problems in a row. What did we forget to do here? Because this is going to be a negative. No, that's a. Actually, no, actually that's okay because it's not negative. But why am I? Something's off by a factor of 2. Why am I off by a factor of 2? What's causing the goof up? Because I can rewrite this piece here. I can take out a 2 and move. No, I'm okay. Never mind. Sorry. Well, maybe I'm okay. At least I know what I did. I'm not wrong. It's okay. This is the same thing as the following. I wrote a to 16 times a half. What can I do with this 1/2? Move it up as an exponent. W to the 1/2 is the same thing as square root of W. So I get 8W natural log of square root of W minus 16W natural log of root W, or negative 8W. I didn't do anything wrong. I just didn't see how I needed to simplify it off the top of my head. So you get A. A was negative, right? That simplifying was a pain. Yeah, Katie.
Can you explain one more time how we know that it comes to a point where x equals 0?
This part here?
Yeah.
Okay, so when x is equal to 0, this completely collapses to 0, and so does this. So any time that x is 0, doesn't matter what y is, I still get the point 0, 0. So it completely collapses that entire line segment to a point. Yeah, Marshall.
Would you accept the 8W ln square root of W minus 8W ln W as some like shape of form, or would you?
Oh, here?
Yeah.
Oh, yeah, yeah, it'd be fine.
Okay.
That would be fine, yeah. I would not expect you to go back through and simplify that. It's hard enough to get to that point. That one okay? Now, it's possible you could have also done with the same ideas that we did before, as opposed to going through the Jacobian. You could have done this with the previous problem as well. We're looking for, remember, we're looking for the PDF of W. So we could have done this like we did before and find the distribution function, the CDF first. So if I said I'll call it capital G of W, this would be the probability that capital W is less than or equal to little w, right? This is how we did the other problems with transformations with one variable, didn't we? W is the same thing as x times y in this case, right? Yeah. And this would be the probability that y is less than or equal to little w over capital X. Right? So let's think about the picture. This is your X, this is your Y, and this is the region that we were doing. Right? We agree? What kind of, if I don't worry about the less than or equal to, and just look at y equals something over x, what kind of a shape does that look like? Say it was 1 over x. What would that look like?
Yeah.
It's a part of a hyperbola, right? So in this case, it would look something like this, depending on what the w is, right? Correct? And we want y to be less than or equal to that, so we would be looking for that region. We agree? Okay. Well, that's kind of ugly to do, right? Right? But I could do it if I really, really, really wanted to. I could do it. I don't really want to. But I could find this one a little bit more easily because I have the same bounding curve on left and right. Right? How can I convert this probability into the other probability? What would I need to do?
1 minus.
1 minus, good. So I could do this as 1 minus the probability that y is greater than w over x. No, I probably want to go this way, don't I? Do that in red. Right? So this would be, I want to integrate with respect to x first and then y. Right? Oops. I still leave my 1 minus out in front here. So your function, your PDF was 8xy dx dy. Right? Your top curve would be y, and your bottom curve would be w over y. And your y's go for, well, your top bound for y will be 1. Your bottom bound will be this intersection point. Right? That's as low as the y's can get, is that intersection point. Well, this is the line y equals x, so you'll get square root of w here. Because you'll have y equals w over y squared is w. Okay? If you go through and do this, this gives you the CDF for w. And how would you get to the PDF from there? Take the derivative, right? You can get there using the same principles. It's just, I think, a little bit more difficult, right? I think it's more difficult than what we did to start with. Okay, it's kind of a pick your poison, right? When you do your Jacobian up here, I still have to integrate one of the variables away, right? To do that, I have to pay attention to where my boundaries are. To this one, I have to differentiate one of my variables away, essentially, right? When I do a derivative, integrating one of my variables away is doing this double integral, get rid of both of the x's and y's to get something in terms of w, and then take a derivative. I still had to worry about where my boundaries were, right? So I'm not sure this is easier. I think this is actually more complicated. You can do it. You can do it either way. Notice that it doesn't make sense to do this for the first problem that we did because it asks for a joint PDF, right? This doesn't give me a joint PDF. This only gives me a PDF for W, right? It only works if I'm asked for one variable in terms of two. I can go back to this, I'll call it first principles idea, get the distribution function, and then take a derivative. I think it's more work, personally. Because I still have to pay attention to boundaries, right? And then I have to do a double integral and take a derivative. Which seems kind of messy. All right. Okay, so we'll do more stuff next time. We will go back to this first principles idea, which is one of the reasons why I talked about it. We will go through this first principles idea does help in certain transformations. In particular, when we talk about what are referred to as order statistics. So what we're going to be interested in doing in the next few sections and pretty much the rest of the semester is what happens to distributions when we have independent random variables and doing them all identically distributed. So we'll talk more about this on Wednesday. Have a good one.
3 minutes, Dr. Joe.